During the previous lecture, we discussed the notion of invertible matrix, and so the definition was that a matrix is called invertible if there exists another matrix, a to the minus 1, such that a to the minus 1 multiplied by a is equal to the identity and is equal to a multiplied by a to the minus 1 from the right. So this was the definition, and as a consequence of this definition, we proved that if such matrix, if the matrix a to the minus 1 exists, then it is unique. So we also discussed that one can consider left inverse or right inverse matrix. So such a matrix that being multiplied by this matrix from the left, we get the identity, and so also when our matrix is multiplied by this a to the minus 1 from the right, it also gives the identity. So sometimes these matrices are called left inverse and right inverse. So we did not prove that for square matrices the existence of left inverse or right inverse is equivalent to the existence of the inverse matrix. So, and now we will prove this. So we'll start with the subsection 3.6, left-invertible and right-invertible matrices. So I will formulate and prove a theorem. Let a square matrix be left or right invertible then it is invertible. Okay, so let us prove this statement. And first I'm going to assume that a square matrix is left invertible. Assume a square matrix A is left invertible so there exists a square matrix L such that L multiplied by A, L multiplied by A gives the identity. Okay, so consider a linear system A multiplied by X equals 0. So I'm going to multiply this relation by A from the left, sorry. So what are we going to get? So I will write it as, I will switch right-hand side and left-hand side of this relation. So 0 equals LA multiplied by x. So we know that L is the left inverse, so this is just the identity multiplied by x, which gives x. So what do we get? Now we see that the only solution to this equation, to this system of linear equation, is the zero solution. So x equals 0 is the only solution to this linear system. Okay. Consider now the reduced row echelon form of our matrix A. So since the solution is unique, there are no free variables, and therefore all variables are leading. And so what can we say about this matrix? So it follows that this matrix is exactly the identity matrix. So the reduced row echelon form of A is the identity matrix. Just because we are talking about square matrices, so the number of rows is equal to the number of columns in this matrix, and since there are no free variables, all the variables are leading, and so according to the definition of the reduced row echelon form, we can come to the conclusion that it is exactly the identity matrix. Okay, but we know that every elementary row operation corresponds to the multiplication by some elementary matrix from the left. So the identity matrix I, which is the reduced row echelon form of A, can be represented as the product of elementary matrices multiplied by A, where so ek, etc. E1. Sorry, I denoted them by U, so I will try to keep the notation from the previous lecture. So where UK, etc. U1 are elementary matrices. So we proved that all elementary matrices are invertible. And therefore, their product is also invertible. So denote their product by B. And so we see that B multiplied by A gives the identity. And since B is invertible, then A is its inverse, and then A is its inverse, and so A is also invertible. So A is invertible to B, and therefore A is also invertible. Okay, so we proved the first part of our statement, that if a square matrix is left-invertible, then it is invertible. Okay, so assume now that A is right-invertible. So what does this mean? So this means that there exists a square matrix R such that A being multiplied by R from the right gives the identity. Okay, so now I'm going to transpose this relation. So we know that transpose to the product is equal to the product of transposes, but in the reverse order. So we get the relation R transpose multiplied by A transpose is equal to the identity, just because the identity is equal to its transpose. Okay, so we see that A transpose is left-invertible. And so since A transpose is left-invertible, according to the previous statement, it is invertible. We already proved this. Hence, A transpose is invertible. Therefore, there exists a square matrix C such that C multiplied by A transpose equals A transpose multiplied by C equals the identity. And now I'm going to transpose this relation once again. So what do we get? We get A multiplied by C transpose equals C transpose multiplied by A equals the identity. So, according to the definition, C transpose is the inverse to A. So A is invertible. So we proved this statement. Okay, so it is enough to show that our matrix is left or right invertible to prove its invertibility. And so we know how to find the left inverse, so we discussed the algorithm during the previous lecture, and therefore this algorithm produces the the inverse matrix. Okay, and so now we know something about invertible matrices and about the inverse matrix, but still we do not know any conditions, any necessary and sufficient conditions for a square matrix to be invertible. So we are moving towards finding these conditions, but first we need to introduce some tools and notions. And so the next section would be about the coordinate vector space. So it would be section 4. Coordinate space R to the n. So the first subsection would be vectors and algebraic operations. Okay, so what is the space R to the n? So as we consider, if we consider it as a set, so it is just the Cartesian product of the set of real numbers by itself n times. So consider the Cartesian product Rn, which is R by R, etc., by R n times. So this set consists of n tuples of real numbers, and we will denote this n tuples not as rows but as columns. So take an element from Rn, so x is just an n tuple of real numbers x sub 1, etc., x sub n, where x1, etc., xn are real numbers. So these n tuples are just n by 1 matrices. Can be interpreted as n by 1 matrices and so we can apply all the things that we know about matrices to these n tuples. Besides, so we will call these n tuples vectors. So we will call the elements of Rn vectors. So why it is natural to call them vectors? Just because if we consider the case when n equals 2, then we get just the Cartesian plane, and so every vector on the Cartesian plane has 2 coordinates, so it can be interpreted as a pair of real numbers, and so this is a vector with 2 components. And if so, we can consider similarly, we can consider just an arbitrary number of vectors here. So we consider the Cartesian product of arbitrary number copies of the set of real numbers by itself, and so in this case our vectors will have n components, and so they are n by 1 matrices, and that's why we can add them to each other, and we can multiply them by real numbers. So let me write this down for just for convenience. So let x and y be two vectors, then, so according to the definition of matrix addition, x plus y is the column vector where the first component is x1 plus y1, etc., xn plus yn. So where x consists of x1, etc., xn, and y consists of y1, etc., yn. And in the similar way, so lambda multiplied by x is just lambda multiplied, or actually this is not the introduction of u notation, just because we are using the notation that was introduced for matrices. So lambda times x1, etc., lambda times xn, where lambda is a real number. So we know how to add vectors, we know how to multiply vectors by real numbers, and just because the elements of Rn are matrices, all the properties like associativity or commutativity are also satisfied for the elements of this set. 4.2 will be linear combinations. So now we need to introduce some terminology in order to use them throughout the whole course. So I will start this subsection with the definition. So let v1, etc., vk be elements of our coordinate space, and let alpha 1, etc., alpha k be scalars, or just constants. Then an expression of the form alpha 1 times v1 plus alpha 2 times v2 plus etc. plus alpha k times vk is called a linear combination of vectors v1, etc., vk. So since we know how to define the sum of any two vectors, and we know how to multiply a vector by a scalar, this is also an element of our coordinate space. Then a linear combination is called trivial. If all its coefficients are zeros. So we can consider the zero vector, which is just 0 by v1, etc., plus etc., plus 0 by vk, and such linear combination is called trivial. Okay. Then let me introduce one more notion. So I'm going to give one more definition. So a subset V in R to the n is called a linear subspace or a vector subspace if the following properties are satisfied. So first of all, for any two vectors x and y from Rn, their sum x plus y also, sorry, not from Rn, for every two vectors from this subset from V, for any two vectors from V, their sum also belongs to V, and for any x from V and for any scalar lambda, lambda multiplied by x also belongs to V. So, I will just add one more requirement. So a non-empty subset, a non-empty subset is called a linear subspace, just because otherwise there is no sense to consider empty subsets, empty subspaces. Okay, so a subset is called a linear subspace if we can add vectors from this set and we can multiply them by scalars. So let me consider some examples. So first of all vectors proportional to some vector from Rn. So all vectors of the form lambda times x, where x is some vector from Rn, and I will consider it to be non-zero. So all vectors of this form form a subspace, just because we can add them, and so they will still have this form, and we can multiply them by scalars. Then the set that contains only of the zero vector is also a linear subspace. In Rn, just because it consists only of the only element. So if we add this element with itself, we also get 0, and so if we multiply this element by any constant, we will also get 0. But we can state that all vectors from Rn with integer coordinates do not form a subspace. Just because if we consider such a vector and multiply it by 1/2, for example, we will get a vector that does not have such form. So the second property is not satisfied for this subset. Okay, so these are subsets of a linear space. And let me say a few words about geometrical interpretation of this. So this would be just a remark. So maybe two remarks. So consider the space R2, which is just our plane, and so what are the subspaces? So this is R2, and so there is 0 somewhere, and I'm going to consider some vector. So as we know, there is always a trivial subset, there is always a trivial subspace that consists only of 0, but now assume that our subset consists some non-trivial element, so let me denote it by V. So consider R2 and assume that a subspace V is non-trivial so it contains some non-zero vector. Then, according to the definition, it should contain all vectors proportional to this vector. So it contains the whole line passing through V. Okay, and as we already discussed, the spaces of this subsets of this form always form a linear subspace. So all the lines passing through the origin are linear subspaces in R2. So if we assume that there is some other vector in this subspace, then it is possible to prove that this subspace coincides with the whole plane. So we will discuss this a bit later. But anyway, all the lines form linear subspaces. And now let us briefly consider the case when n equals 3. So if n equals 3, then all lines in R3 passing through the origin and all planes passing through the origin are also linear subspaces. So I'm going to consider the coordinate space R3, and in this case every plane passing through the origin, so every plane of this form forms a subspace, just because the sum of every two geometrical vectors. So here I'm going to consider the picture. So, but if we are in the space R3, then every geometrical vector, this is the directed segment, so it has coordinates, it has 3 coordinates, and that's why one can assign to every geometrical vector a column of its coordinates of this kind, and so these are the same objects. So when we consider the sum of 2 vectors, then it also belongs to this plane. That's why the first property is satisfied, and if we multiply a vector from this plane by some scalar, then the result also then the result also belongs to this plane. So every plane passing through the origin also can be referred to as a linear or a vector subspace in the space R3. One more definition. So let V1, etc., Vk be a family of vectors then the set of all linear combinations of V1, etc., Vk is called the span of V1, etc., Vk. So the notation is like this. So we put just angle brackets, and so this is the space of all vectors from Rn such that V has the form alpha 1 times V1 plus etc. plus alpha k times Vk, where alpha 1, etc., alpha k are just real numbers. So the set of all linear combinations of vectors from this family is called the span of V1, etc., Vk. So now we'll formulate and prove a rather simple proposition that the span of every non-empty family of vectors in Rn is a linear subspace. So the proof is quite simple. So consider 2 elements from the span. Then there exist alpha 1, etc., alpha k, and beta 1, etc., beta k from the set of real numbers, such that x equals alpha 1 times v1 plus etc. plus alpha k times vk, and y equals beta 1 times v1 plus etc. plus beta k times vk. Okay, so I'm going to add up these two relations, and so obviously I get the relation that x plus y equals alpha 1 plus beta 1 times v1 plus etc. plus alpha k plus bk times vk. So the sum of x and y also belongs to the span of our family of vectors, just because it can be represented as a linear combination of vectors v1, etc., vk, with the coefficients that are just sums of the coefficients of vectors x and y. So similarly, lambda multiplied by x is lambda alpha 1 times v1 plus etc. plus lambda alpha k times vk, and so it also belongs to the span of v1 etc. vk. So this proves our proposition. 4.3, linearly dependent and linearly independent vectors. Definition. So a family of vectors v1, etc., vk from our coordinate space is called linearly dependent if there exist alpha 1, etc., alpha k from the set of real numbers, such that at least one of them is non-zero, and alpha 1 multiplied by v1 plus etc. plus alpha k multiplied by vk equals 0. So a family of vectors is called linearly dependent if there exists a non-trivial linear combination of these vectors equal to 0. So non-trivial means that at least one of the coefficients is non-zero. So in the same way, a family of vectors v1, etc., vk is called linearly independent if the relation alpha 1 v1 plus etc. plus alpha k vk equals 0 implies alpha 1 equals alpha 2, etc. equals alpha k equals 0. So if only trivial linear combination of these vectors can be equal to 0. So this is the definition, and now let us consider some examples. So the first example, any pair of collinear vectors in R2 or in R3 is linearly dependent. Just because there exists lambda, there exists real number lambda such that u equals lambda times v. So if I move everything to the right-hand side, so to the left-hand side, sorry, I get u minus lambda v equals 0, and so I get a linear combination that is non-trivial. So any triple of coplanar vectors in three-dimensional space is linearly dependent are non-zero then any vector of this triple can be represented as a linear combination of the others. So W is alpha times u plus beta times v for an appropriate pair of real numbers alpha and beta. So geometrically this looks like this. So I'll just consider some plane. In three-dimensional space, and so I have three non-zero vectors there. So u, v, and w. So w can be represented as the sum of vectors. So this should be parallel to u. So let me just sketch this in a more accurate way. So I have the vector w, and I'm going to represent w as linear combination of u and v. How to do this? So I sketch the line that is parallel to the line that contains u here, and then I sketch the line that is parallel to the line that contains v. And I consider vectors of this form. So this vector is alpha times v, and this vector is this vector is alpha times u, and this vector is beta times w times v. And so w is the sum of these two vectors. So this would be alpha times u, and this vector would be beta times v. So every vector w in this case can be represented as the sum of these two vectors. And so if at least one of them is zero vector, then we just have a pair of vectors, so they are in some subspace, and maybe I will discuss this a bit later, what happens if a family of vectors contains a zero vector. Okay, so any triple of coplanar vectors is linearly independent, and we can say, and the converse is also true, that a triple of vectors in R3 is linearly dependent if and only if these vectors are coplanar. And then I can say that any four vectors in R3 are linearly dependent. Okay, so this is more or less, all these statements are more or less geometrically obvious, so I will not go into details, but I will make one remark. So assume a family v1, etc., vk contains a zero vector. Contains a zero vector. Then it is linearly dependent. So why? Just without any loss of generality, I can assume that the last vector is the zero vector. So assume that vk is zero, then consider a linear combination of the form zero multiplied by v1 plus 0 multiplied by v2 plus etc. plus 0 multiplied by vk plus 1 plus alpha, which is non-zero, multiplied by vk. So this is 0 just because vk is 0. So the whole expression is 0, but this linear combination is non-trivial because at least one of the vectors is non-zero. So according to the definition, this family of vectors is linearly dependent. So going back to one of our examples, so if at least one of the vectors is 0, then the whole family of vectors is linearly dependent. Okay. And now I'm going to prove a theorem which states some properties of linearly dependent and linearly independent family of vectors. So there will be 6 statements. All of them would be important, so I will just state all of them. So the following properties are satisfied. So the first property, so any family of vectors in Rn containing a linearly dependent subfamily is also linearly dependent. Okay, any subfamily of a linearly independent family of vectors is also linearly independent. Okay, then what's next? So number 3. Let v1, etc., vk be a linearly dependent family. Then there exists a vector in this family that can be represented as a linear combination of the others. The fourth property is that if some vector in the family v1, etc., vk is a linear combination of the others, then this family is linearly dependent. Okay, so then number 5, let v1, etc., vk be linearly independent and assume the family v1, etc., vk and vk plus 1 is linearly dependent. Then vk plus 1 is a linear combination of v1, etc., vk. Also about linearly independent vectors, so let v1, etc., vk be linearly independent if vector vk plus 1 is not a linear combination of v1, etc., vk, then v1, etc., vk, and vk plus 1 is linearly independent. Okay, so we have these 6 properties, and in fact it takes more time to formulate these properties than to prove them. They are more or less obvious, so let us go briefly through the proof. So what about the first one? So any family of vectors containing a linearly dependent subfamily is also linearly dependent. So consider a family of vectors v1, etc., vk, and so it consists it contains some linearly dependent subfamily. So without loss of generality, assume that subfamily v1, etc., vl is linearly dependent for some L less than k. Then there exist alpha 1, etc., alpha L such that alpha 1 times v1 plus etc. plus alpha L times VL equals 0, and not all of alpha 1, etc., alpha L are zeros. So this follows from the definition of linearly dependent family of vectors. And so now consider alpha 1 times v1 plus etc. plus alpha L times VL plus 0 times VL plus 1 plus etc. plus 0 times VK. So this is also 0, just because we add zeros here. And so we can consider all these zeros as alpha L plus 1, etc., alpha K. Right? So now we have a linear combination of vectors from v1 to vk that is equal to 0, and this linear combination is not trivial because here we have at least one non-zero coefficient. So we conclude that vectors v1, etc., vk are linearly dependent. Okay, so this proves the first part of our theorem. So the second part, so here we have a linearly independent family of vectors. So consider linearly independent of vectors v1, etc., vk, and we need to consider some its subfamily. So once again, without loss of generality, consider a subfamily that consists of vectors from V1 to VL. So without consider subfamily, consider the subfamily V1, etc., VL, and assume it is linearly dependent. Then there exist alpha 1, etc., alpha L, such that not all of them are zeros, and alpha 1 times V1 plus etc. plus alpha L times VL equals 0. So exactly as in the previous case, it follows that 0 equals alpha 1 times V1 plus etc. plus alpha L times VL plus 0 times VL plus 1 plus etc. plus 0 times VK. And so we come to a contradiction. So this proves the second part of our statement. Okay, so what is the third part of our statement? So let V1, etc., Vk be a family, be a linearly dependent family of vectors. Then there exists a vector in this family that can be represented as a linear combination of the others. So let V1, etc., Vk be linearly dependent, sorry. So there exist alpha 1, etc., alpha k, such that alpha 1 times V1 plus etc. plus alpha k times Vk equals 0, and at least one of the coefficients is non-zero. So assume alpha I is non-zero, where I is from 1 to k. So then we can divide the whole relation by alpha k. By alpha I, sorry. And so what do we get? We get Vi can be represented as minus alpha 1 divided by alpha I times V1 minus etc. minus alpha sub I minus 1 divided by alpha I times V sub I minus 1 minus alpha sub I plus 1 over alpha I times Vi minus etc. minus alpha k over alpha I times Vk. So I just divide by alpha I and move everything to the right hand side, so we get this relation, and hence Vi is a linear combination of the others. Okay, so this proves the third statement of our theorem. So the fourth statement, so if some vector is a linear combination of the others, then this family is linearly independent. So without loss of generality, assume that Vk is a linear combination of the others. So we can write down Vk as a linear combination of V1 plus etc. plus Vk minus 1. Okay, so this is equivalent to the relation alpha 1 times V1 plus etc. plus alpha k minus 1 times Vk minus 1 minus Vk equals 0. And so here we have a linear combination that is definitely non-trivial, just because here we have alpha k, which is equal to 1. Right, so this is non-trivial, so it is non-zero, and that's why this linear combination is non-trivial. Okay, so so the family of vectors from V1 to Vk is linearly independent. Okay, so the fifth property. So here we have a linearly independent family, and we add one vector, such that after adding this vector we get a linearly dependent family. Since vectors v1, etc., vk plus 1 are linearly independent, sorry, are linearly dependent, there exist alpha 1, etc., alpha k plus 1, such that alpha 1 times v1 plus etc. plus alpha k times vk plus alpha k plus 1 times vk plus 1 equals 0. So note that this coefficient is non-zero, because otherwise the family of v1, etc., vk is linearly independent. So okay, so this element is so this coefficient is non-zero, so we can express vk plus 1 as a linear combination of the others, so minus alpha 1 over alpha k plus 1 times v1 minus etc. minus alpha k over alpha k plus 1 times vk. So this proves the fifth statement, and now let us move on to the last statement. So here we assume that vectors v1, etc., vk are linearly independent, and when we add a vector that is and we add a vector that is not a linear combination of the first k vectors, then we need to prove that the new family is linearly independent. Okay, so assume the family v1, etc., vk plus 1 is linearly dependent. So I will be very brief. So there exist alpha 1, etc., alpha k plus 1, such that alpha 1 times v1 plus etc. plus alpha k plus 1 times vk plus 1 equals 0. Okay, so we need to come to a contradiction. We know that alpha sub k plus 1 is non-zero, just because otherwise v1, etc., vk are linearly dependent. Okay, so we divide by alpha k plus 1, and so we get the relation that vk plus 1 equals minus alpha 1 over alpha k plus 1 times v1 minus etc. minus alpha k divided by alpha k plus 1 v k. So we come to a contradiction. Okay, so this proves the theorem. So all these proofs are very similar to each other, but nevertheless these statements are very important and we will use them widely within the frame of this course. So it would be 4.4. Basis in a subspace. Okay, so we'll start with the definition. Let V be a linear subspace then a linearly independent family of vectors v1, etc., vk from this subspace is called a basis in V if the span of these vectors is equal to V. So in other words, we can say that a linearly dependent family forms a basis in a subspace if every vector from this subspace can be represented as a linear combination of vectors from this basis, from this family of vectors. So in this case, a family of vectors is called a basis. So let us consider some examples. Consider a span of some non-zero vector then the system that consists only of V forms a basis in V capital. That's quite obvious. Okay, then any family, any pair of non-collinear vectors vectors on the plane forms a basis in R2. So that's more or less obvious. So consider R2. So here we and a pair of non-collinear vectors. So v1 and v2, and for any vector w, so as we did before, we can just draw lines that are parallel to the lines that contain v1 and v2, like this. And so we can represent vector w as a vector that is parallel to v2 plus a vector that is parallel to v1. So this would be alpha 1 times v1, and this would be alpha 2 times v2. So every vector can be represented in this form. So any pair of vectors in every pair of non-collinear vectors on the plane forms a basis in R2. Okay, and then maybe it is rather a terminological remark than an example, that the empty set forms a basis in the trivial subspace Okay, so sometimes it makes sense to consider the empty set as the basis in the trivial subspace, because there are no vectors that should be represented as linear combinations of vectors from the basis. So now we're going to prove a very important lemma. So let v1, etc., vk be a basis in a vector subspace v in Rn. Let w1, etc., ws be a linearly independent family of vectors in V. Then S is not greater than K. Okay, so proof. So since v1, etc., vk form a basis in V capital, every vector w1, etc., ws can be represented as a linear combination of v1, etc., vk. So what does this mean? That there exist coefficients alpha sub ij such that w1 equals alpha sub 1 1 times v1 plus etc. plus alpha sub k1 times vk, and so on. Ws equals alpha sub 1s times v1 plus etc. plus alpha sub ks times vk. So we know that there exists such coefficients. So alpha sub ij are just real numbers. Okay, so assume the contrary. So assume that S is greater than K, and consider a linear combination of vectors w1, etc., ws. So x1 times w1 plus etc. plus xs, plus xs times ws equals 0. So we assume that this linear combination is 0. So since w1, etc., ws are linearly independent, this linear combination has to be trivial. So this means that all coefficients are zeros. Okay, but let us substitute the expressions for w1, etc., ws into this relation. So what are we going to get? So 0 equals x1 multiply the expression for w1. So alpha sub 1 1 times v1 plus etc. plus alpha sub k1 times vk plus etc. plus x s multiplied by alpha times 1s multiplied by v1 plus etc. plus alpha times alpha sub ks times vk. And now I'm going to rewrite this linear combination as a linear combination of vectors v1, etc., vk. So I'm going to get x1 times alpha 1 1 plus etc. plus xs times alpha sub 1s multiplied by v1 plus etc. plus some coefficient multiplied by vk. So this coefficient equals to x1 multiplied by alpha sub k1 plus etc. plus xs multiplied by alpha sub ks multiplied by vk. So linear combination of these vectors is 0. So since v1, etc., vk are linearly independent, all coefficients are zeros. So we get a system of linear equations. So alpha 1 1 times x1 plus etc. plus alpha sub 1s times xs equals 0, so on. Alpha times k1 times x1 plus etc. plus alpha times alpha sub ks times xs equals 0. So we come to this linear system. So consider the matrix of this linear system. So A is a matrix with k rows and s columns, and with real entries. Okay, so according to our assumption, s is greater than k, so the number of columns in this matrix is greater than the number of rows. Okay, consider the reduced row echelon form of A. So, since the number of columns is greater than the number of rows, so not all so there exist free variables. Okay, so this system is consistent since it admits trivial solution. Obviously, if we set all x's to be 0, we get the solution. Okay, so it is consistent, and due to the fact that there are free variables, the solution is not unique. So the existence implies the solution is not unique. Hence, there exists a non-trivial solution. But we started from the fact that we consider a linear combination of vectors w1, etc., wn that are linearly independent due to our assumption. And so we get a linear combination of these vectors that is non-trivial. So we come to a contradiction. So this proves our lemma.